let's recall shortly that what we did. So we consider gyroscopic systems. So this is a system which in linearized form, it takes this structure where G, which before was dissipation term, now it's a term. So what happens now, the matrix, mass matrix is still symmetric, but G is anti-symmetric term. C is still symmetric. So what we did, we consider example. Example which is mass which is attached to a rigid frame. So we take a rigid frame which is rotated with certain velocity. So omega is rotational velocity, and then the mass is suspended in the middle. So in the middle, so which means that it's suspended on the elastic springs. So the springs at each direction. So mass m, and we had two springs. So there are two directions: direction x and direction xy and x2, which are fixed to the frame. So it's a coordinate system which is attached to the frame. And then we have coordinates x1, x2 is the coordinates of the mass, and we have two springs of one coefficient and two springs of another coefficient. So the springs in different directions are different. Right? So springs are different. We're discussing that this may be a kind of simple model of the washing machine, that horizontal washing machine that we have here. So we have a central part which is rotating, and it has some stiffness. So it rotates and oscillates with some springs. So usually here the asymmetry is produced by the mass asymmetry, but here we produce this asymmetry by the stiffness asymmetry. So that qualitatively it gives the same result. So what we did, we found that the equation of motion, so we can write Lagrangian equations for the system, and the system that we get at the end. So we have the vector q as x1, x2, two coordinates of the mass, and then we have exactly this system. So equilibrium is 0, 0. So when the mass is rotating just in the middle, because when mass is in the middle, the rotation doesn't make any effect. So it stays at the same place. And the equation of motion out of this form, where what we found, so at the end we found the following structure. We found that after dividing by m, so we found that mass matrix can be just taken as identity. G matrix is zero minus 2 omega 2 omega 0, and you see it's antisymmetric, right? Because he's minus and plus. And then we had the C matrix, which had the form of omega 1 squared 0, 0 omega 2 squared. I'll tell what it is, plus minus omega squared 1, 1. Okay. So that's what, so what is omega 1? Omega 1 squared is 2 k1 over m, and omega 2 squared is 2k2 over m. So this is exactly the frequency of oscillations. So if there is no rotation, then omega 1 will be frequency of the oscillation in this direction. Remember, k divided by m is the frequency of harmonic oscillator. We have two springs, so it will be 2k1 over m. And the same in the second direction. So these are eigenfrequencies. So essentially, what is what? So this is elastic force. The elastic part. This corresponds to the centrifugal. So it's minus, so it's a force which tries to, when there is rotation, force that tries to pull it out. And this is what we know as Coriolis. This term which gives you Coriolis force, so this term which is proportional to speed. So essentially, it's if something moving. So when you're in a centrifuge, when you start to walk toward the center, you will be pulled to the side. So this is Coriolis force. So there are three classical forces. So what we next have to do is to find eigenvalues. In order to understand, so the solution of the system is given determined by its eigenvalues. So what eigenvalues are given by the determinant of this characteristic equation, by determinant of this matrix, which is a characteristic equation, called 0. So let's write this matrix. So it will be determinant of, so the mass matrix gives you lambda squared here and there. Then the G gives you minus 2 omega lambda here, minus 2 omega lambda. And C gives you plus omega 1 squared and minus omega squared. So this is it. And this here will be plus omega 2 squared minus omega squared. So omega is rotation velocity. Omega 1, omega 2 are natural frequencies of the system. So this is a product of these terms minus these terms. So you get minus by minus plus, it will be plus 4 squared. Okay, so open it up. No good. No, it's okay. Yeah, it's fine. So open the product, lambda 4 plus, so there will be the product of these two plus 4 of this. So what it will be, the product, it will be omega 1 squared minus omega squared plus, omega squared, and then there is this 4 lambda squared. So this is omega 1 squared plus omega 2 squared, and then you cancel this with plus 2 omega squared. And what's rest is omega 1 squared minus omega squared by omega 2 squared minus omega squared. Good. So this is 0. So we now with a quadratic equation with respect to lambda squared, so we find lambda squared. So it minus this term. So let's take this term over 2. So it will be, I will start writing from this side on. So plus 1 squared plus omega 2 squared over 2. Plus minus, and this is square of this term minus over divided by 2 minus this, right? So square of this left term minus this. Okay. So what's left? So what we will do here is so how you do it easier. Okay, you just open this product. So open this product, so it will be lambda square minus omega squared plus omega 1 squared plus 2 squared over 2 plus minus squared. So when you open, you see omega fourth order will cancel with this omega fourth order. So the first term will be omega squared, which gives this sum and this. So it will be 2 omega 1 squared plus omega 2 squared omega squared. And then there will be just a term which does not depend on omega. So it will be this squared minus over 4 minus that, which is just same as difference squared. So you can check that this is true. So that's the result. And what is good is that this is real, and square root is positive, right? Because everything is positive. So it's omega squared is a real number. So at least omega squares of the eigenvalues are real. They are real, and what we can be interested in. So if they're real, what is important if it's positive or negative? Because if it's positive, then lambda will be real, because it will be square root of positive number. But if lambda squared is negative, then lambda will be imaginary. And this is very different behavior. So we need to find when lambda is 0. Okay. So lambda is 0 if this square equal to that square, I'm not sure we need. So this is 0, certainly when you take plus, right? And when square of this equal to square of this. So if omega square plus omega 1 square plus omega 2 square over 2 equal square equal to okay. So you can solve this equation because it's also quadratic in omega square. But since it's quadratic in omega square, we know that there can be just 2 solutions. And you can guess these 2 solutions. So there are 2 critical solutions. One is omega 1 square, another omega 2 square. So you can just check substituting omega 1 square that for omega or omega 2 square. So you can choose, put this value for omega square and see that it's satisfied. So we find 2 critical values. So essentially what we did is we can plot now. We can plot the result. So it's more convenient to plot lambda square as function of squared velocity, because only velocity comes squared. Squared is clear because it doesn't matter in which direction it will rotate, the eigenvalues should be the same. So when omega is 0, you get here 0 and 0, And you see that there will be, so when omega is 0, lambda square will be, one of them will be 1 minus omega 1 squared, another will be minus omega 2 squared. As it should be, because without rotation is just oscillation. So we put here 0, put here 0, then we can take square root. Sum will give, difference will give minus omega 1 squared, sum will give minus omega 2 squared. So there will be two values here. Minus omega 1 squared, minus 2 squared. Then, so what you can see, when omega is increasing, so if you take the, omega is increasing, this term is getting bigger, and this term is getting bigger. So if you take minus and minus, then lower eigenvalue will just go down, right? So it's always decreasing by taking minus and minus. But if you take plus, what you should have, you should change, this function should go through these two roots. So the lambda square will become 0 at 1, this omega 1 squared and omega 2 squared. So there are, we know that this should pass through these 2 points. So that's the shape of the solution for square. And now we can plot eigenvalues themselves. So eigenvalues are complex, right? So because square is negative. So what do we have? So at the 0, so at initial, when there is no rotation, we have two negative values. So we have two purely imaginary. It gives you two pure imaginary roots. So it's I omega 1, I omega 2. So this is at no velocity. And there will be plus and minus, right? So there will be, so lambdas which are obtained as square root of these 2 points, this gives you 4 imaginary numbers. Then for the lower one, so let's write it in red. For the lower one will just increase in absolute value. So these two, they just upper gives up, lower goes down, following imaginary axis. And for the upper eigenvalue, let's put it in blue. The upper eigenvalue, it comes to 0, which means that the two imaginary, the square goes to 0, so the eigenvalues themselves also go to 0. This is first occurs at omega 1. Then square becomes real. It means that the solution is real, positive and negative. So the two eigenvalues come to different side, getting some values, and then go back to 0. So it's something like this, symmetrically. And they come again at rotation velocity omega 2. And next they become imaginary, so they also split onto the imaginary axis. Good. So what do we have? So when our rotation velocity is between these two eigenfrequencies, in that case we're on the situation of this loop. So there is one eigenvalue which is positive. Yeah. There's eigenvalue on the right-hand side, and we know by the Lyapunov theorem that it's unstable equilibrium. So when omega squared is smaller than first eigenfrequency or bigger than all eigenvalues, real parts of eigenvalues are 0, and lambdas are simple. Remember that each one has there are no Jordan blocks. So all are 0 and lambdas are simple, which means that the equilibrium, which means that equilibrium of linearized system is stable. And this is what you can observe many times. So when you have a washing machine, it starts. When it rotates slowly, it's stable. But there is certain velocity, then it suddenly starts to shake. So what happens is that motor tries to pass this increased velocity further on, because the velocities when it starts to shake is exactly this interval between omega 1 and omega 2. And then if you succeed to increase velocity fast enough, then it becomes stable again. So that's an idea, and that's an idea of the accelerating washing machine. So if you accelerate washing machine very, very slow, it will not be stable. At certain frequencies, it starts to vibrate. So that's why it starts to accelerate faster, so that regime will pass through. Sometimes, if the difference between omega 1 and omega 2 is very, very large, so there is big asymmetry of what is happening, it does not succeed. So it starts to shake. You can even see it. I have a small experimental device. So this is for making cappuccino. Yeah, so if you remember, if you have. So this is exactly the system that we have. So there is a mass. It's elastic, so there is elasticity. It's never symmetric, so it's almost symmetric, but there is slight difference between omega 1 and omega 2. And it's stable, right? So you put it, and it's perfectly well. So what I will try to change the velocity of rotation. And you will see that, so for example, if you, so I will decrease the velocity of rotation, and we will see this interval. So I will try to make it slower. And you see that there is this interval of velocities where it's unstable, so it's shaking. If I'm doing slower, even slower, it's difficult. Even slower is becoming more and more stable. So it's essentially when it's slow enough, it should, it's becoming, starts to rotating stably enough, right? Okay. You can play with this. Okay, so then the next remark is that, however, this case, in the stable case, we have a real part equal to 0, which means that we are in the Lyapunov special case. So when we're in the Lyapunov special case, we're not sure. This does not guarantee that the system is stable, since all what we did is we studied stability of linearized systems. So in the special Lyapunov case, what can happen is that the stability may depend on nonlinear terms, or if you add small dissipation or dissipative terms. So whatever you add, nonlinear terms or dissipative terms, they can all change stability to instability. So first case we're sure, the second case we're not sure. Experimentally, we see that it's all right for this device, but in principle, you should be careful because that may be not true. And that happens to be not true. So let's summarize what we did, but in more general terms. So what is gyroscopic system? Gyroscopic system gyroscopic term is G Q dot with G being asymmetric. So we found from this example that it appears in a Lagrangian formulation written in a rotating reference frame. So this is something we never did because every time when we were considering the generalized coordinates, remember the generalized coordinates was some vector q, which defines positions of all material points as function of q, right? So when you're in a rotating reference frame, the positions actually depend on q and on time, because every time a reference frame is in different positions. So that this is a slightly more general definition of generalized coordinates, which include also time in the transformation. And in that case, it turned out that we obtained this term, which, as we show in the example. So now just let us show that the system, the gyroscopic system, this system is obtained using a Lagrangian function, which is just half of velocity. Let's not write deltas. So velocity squared or velocity transposed velocity. So this is usual kinetic energy. But then what we do, we put extra term which mixes velocities with coordinates through the G matrix, and minus the usual term which corresponds to potential energy. So let's just write all the Lagrange equations, and we'll see that we come to this equation. And that it just proves that gyroscopic systems, they're the same conservative Lagrangian system, but just written in special reference frame, where we not only define generalized coordinates as a function of q, but q and t. So how you do? So Lagrangian. So let's write just Lagrangian. Remember, so let's write it in component form. So Lagrangian is 1/2, and then there will be sum jk from 1 to n. And there will be mass ij, or jk, mass component qj dot qk dot, then this gives you plus jk, so this is component of matrix G, but it on one side it's multiplied by velocity, on another side it's multiplied by coordinate, and then minus the last one, c jk qj qk. Okay. So we need to write Euler-Lagrange equations, so let's remember how we do. So how you take a derivative with respect to velocity. So it will appear here when I equal j, it will appear here when k equal, j equal I, this appears here when k equal I, and it also appears here when j equal I. So there will be three sums. So it will be 1/2 first sum. So let's take when it's k equal I. So it's j will remain. J and k equal I, right? So q, j. Second sum will be when j equal I, so k remains. And plus this sum we differentiate when I equal, well, j equal I, so it's in k. Like this. And we, remember that we take this sum together because M is a symmetric matrix, so we change k to j and then switch this value, so it will become mij qj. And also we can write, instead of k, we can write j. So it will be ij qj. Okay, so this is the term we found. And in the same way you find the other one, so it appears from this component, from this component, from this component. So already let's write the results. It will be 1/2. So it will be 1/2 of the. So I'll write the result just directly. So it will be 1/2 of j when k equal when k equal I, so it will be ji. This minus so that's from the two terms the same thing you do. Do the same step, you get to this expression. Just check it. And then the Euler-Lagrange equation is d dt dl dq I dot minus dl dqi equals 0. So you differentiate the first by time and subtract the second. So when you differentiate the first by time, you get mij qj second derivative. Then it will be plus 1/2 gij qj derivative. And then we subtract this, right? So it's minus minus 1/2 GGI QG and plus CIJ QG equals 0. But now remember that G is asymmetric matrix, so Gij is minus GJI is minus Gij. Yeah, this is the condition. So at the end, this term is just 1/2 cancelled. This term is just Jij Qj dot. And what is written here is exactly in a matrix, in a vectorial form. It is exactly what we need. So exactly that equation. So what we prove here is that gyroscopic system is just Lagrangian system, just written in usual form. Written in usual form, but with different Lagrangian. With Lagrangian, which has one extra component, which depends. The Lagrangian is slightly more complex. So there is this extra component where you mix velocities of coordinates, and this term appears in usually implication from the rotational reference frame. So what we can comment? So what we can comment is that, in principle, unlike dissipative term, gyroscopic terms can stabilize a statically unstable system, which means that C is not positive definite. Remember, so something like a situation of the inverted pendulum. So in order to see this, so see that this our example. In our example with this mass, this matrix C was what? Was omega 1 square minus omega square 0, 0, omega 2 square minus omega square. So what you have is that there are two stable situations. So if omega square is smaller than omega 1 square, so I don't remember if I said that. We choose 1 smaller than 2. So in this situation, both values are positive, and C is positive, positive definite. But in the in the second stable situation, that's case when the system is accelerated after the instability. So both values are negative. So essentially what happens is C is negatively definite. So in that case, the system should not be stable just by potential forces, but the gyroscopic forces, they can stabilize. And this is what, remember, we proved that dissipative terms cannot do. So dissipation cannot stabilize something unstable, but gyroscopic rotation can stabilize something unstable. So then we get to many interesting applications when the system becomes gets stabilized by gyroscopic terms. This is used in engineering, but the simplest example that you should remember from playing in childhood is a top. So remember that when you have this, the top, and you just rotate it. I'm not good in. drawing. So you take the body with the tip and you just rotate it. If you rotate it fast enough, it will not fall. And clearly, this is a situation which is unstable just statically. If you just put it stably, just put it without rotation, you have forces which just. So this is still equilibrium, but it's unstable. So if you rotate, it can get stabilized. And this is more or less the same stabilization that we had in our example at very large forces. So the symmetrics is negative. So just with the symmetrics, it would be unstable. But because of the gyroscopic forces, it's stable. However, this is always this what's called gyroscopic stabilization. Is always a Lyapunov special case. So so stability depends on nonlinear and, if any, small dissipation terms and dissipation terms. So when you take into account, if you just make a linear analysis, linearization, you find it stable, but nonlinear terms that you neglected, or maybe very, very small dissipations that you can put, they both can destabilize the system, and this is important. So you don't have a you have a gyroscopic stabilization from linearized system, and it often works. But in order to make it rigorous and you guarantee that it's stable, you have to do much more complicated analysis. Just to mention the example where it didn't work. So there was what I remember, there is this satellite was done in, remember, 98, 99. No, 50, in 50. So there was a satellite which is called Explorer 1. Explorer 1. American. And the idea was that, so the idea of the satellite is always you send it to orbit and it should stay. Right, so you should communicate, and it should stay preferably in fixed position. But it's very complicated to make control. So the best is that if you launch it and it stays in the right position without doing anything, just by itself. So then there is a difficult question of stability. So how to make the position to be stable in certain, how to make satellites stable in certain positions. So their idea was to make it in the form, I may draw it wrongly, but the idea is that make it long, the form of cigar, and rotate. And then it becomes, it gets stabilized by rotation. So just in a similar way as we did. And there was antenna attached. So this satellite was not stable. So the question is there's very small dissipation because of the motion of antenna. Antenna dissipated in energy a little bit, and very small influence, because this is a Lyapunov special case. Very small influence may at long time destabilize the system. So it starts to roll, and essentially it lost its stable position. So that's why the Lyapunov special case is always good to remember that it exists. Okay, so good. Let's make short break and then we go. So we continue. Break. till 11. Because we have important problem to solve. Maybe even shorter. Okay. Obrigado. Okay, so now we consider the system which is kind of truly non-conservative. We already had a non-conservative system with dissipation, but now we will consider something more dramatic. So it will be non-conservative. And in that case, what I already called circulatory. This is name which is appearing in literature, not extremely common, but appears of forces, so non-conservative circulatory forces. So we will add now to our system the forces which depend on positions. So this matrix N is an antisymmetric matrix which multiplies the coordinates. So N is antisymmetric. So I already told that this is the origin of this type of forces is often aerodynamic. Dynamic force, which contributes to N, C, and often it contributes also in the velocity-dependent terms as well. But we will consider some simple model, and essentially let's consider just one example. Which is shows how everything works. One example. And we will consider the very important in design of aircraft the phenomenon which is called flutter. Flutter means that something is fluttering. So this is phenomenon you can see all the time. Not all the time, but often you can see in the window. So when there's a wind, the leaves, they start to oscillate, right? So the question, why leaves oscillate? And they oscillate stably. Sometimes if you have wind, some part of the curtain oscillates. So you see that wind is constant, so there is no periodic motion outside. So just there is a constant wind, but the leaf or any other thing, they start oscillating. It keeps oscillating as long as the wind is blowing. So let's see why it happens. So we will consider. Let's try to make a model which we can solve by hand. So consider the wind. This will be our wind, or velocity v. And it is blowing on a leaf. So we have a leaf, and it's supported. So if it's there is no wind, it's just straight. Right? Assume it's straight. So we will model the leaf by a rigid plate. Okay, just rigid plate, the leaf, the wind, and the leaf can go up and down, right? So it's supported. So it can go up and down, and it can move, change the angle. So we define the angle, and also we define the position of the left point by coordinate y. So this is putting 0 somewhere. So the position of the leaf is defined by the height of the left point and angle. So this is how it can move. So this is the leaf. So if you just change position, it goes up and down. But if you change angle, it rotates. And if you change both, it can make this type of motion. Okay, so this is it. As I said, that it's supported. So usually there is a force which is trying to put it back to the equilibrium, the elastic force, and also trying to keep it straight. So we will consider two springs. One spring which is supporting the left end, and another string we'll consider this string which tries to keep it straight. Right? So there is a stiffness in this for rotation, and there is a stiffness for going up and down. There are two strings, and the equilibrium is at y0, phi0. So if no wind blowing, and you can put the system in straight position and it stays. But if you change it a little bit, it will oscillate because there is a spring here with, so which one? So this is with coefficient K1, and this will be coefficient K2. There are two springs which support this whole system. Okay. No gravity, so let's forget about gravity. We have to describe this rod. So this rod has a mass m and length L. Okay, so the length is L, mass is m, and then finally we need to see what is the action of the wind. Well, so action of the wind. So we will use a simple model which just tells you that there is no force if it's straight. So it means that the force can be taken proportional to angle. So angle is positive, the force is pushing down. If negative, force pushing up. So we take a force, we put it straight in the middle, and call it aerodynamic force. So the force is applied in the middle. And so aerodynamic force. So we take, this is probably the simplest model that we can take. So the force, the value of the force is proportional to phi. And also it's should depend on velocity. So the simple model which, the good model, for, at least for large velocity, so the good model is it proportional to squared of velocity. Like this. And then there is coefficient which you can just try to measure experimentally, Ca. So this is aerodynamic coefficient. So the force is composed by aerodynamic coefficient squared of the velocity and angle. No velocity, there is no force if there is no velocity of if there is no wind, or there is no force if the plate is just looking in direction of the wind. So that's our model. That's it. So the first step is writing equation of motion. So the first part is the kinetic energy. Well, in order to find kinetic energy of the rigid body, there is a theory about the motion of rigid body. I didn't give it to you. So we'll just derive it in a way which we know. So what you have, let us consider a point at a distance x, which is between 0 and L. So we consider point of the at distance x. Between 0 and L, right? So this is our body, and we consider point at the distance L, x. So what is the velocity? Its velocity is, so we can find the velocity. Velocity of this, its velocity is what? It can be composed by motion of the left end plus also the rotation. and it gives us phi dot x. So at small angles, velocities look at the same direction. So velocity approximately can be taken as y dot plus x phi dot. So at for small phi. You can do it in a more rigorous way. This will be then just linearized part of the velocity. So the velocity is at that point is the velocity of the left point plus the rotational velocity. Okay, so then the kinetic energy of this piece is, remember what is the velocity squared by mass, by 2, and by mass. And mass of this small, so let's consider this small piece of the size dx. Then the mass will be dx over L is a piece, what is the fraction of the whole body we consider by m. Right? So this is kinetic energy of this small piece of our body, and then if you want kinetic energy of the whole, you have to take integral from 0 to L. So this is how you derive kinetic energy, but in principle you should derive it directly from this when you know mechanics of the rigid body. But let's compute it from here. So we put this expression. So what we can do, we can put m over L outside, n over 2. And then there will be integral from 0 to L v squared. Dx. So open the parentheses. So it would be y dot squared dx. So this one integral, another will be with x plus 2. So okay, let's write it 1 and then y squared plus 2 y dot phi dot x plus phi dot squared x squared dx. And then you know what is what. So integral from y dot squared dx. So y dot is just, so y dot squared is a coefficient, and integral of dx is L, right? Then integrating 2x dx gives you x squared. So this here you get L squared. Right? And here it will be integral of x squared dx, which gives you L cubed over 3. Remember? Good. Let's just open up the expression. It will be m over 2 y dot square. So this is S if the kinetic energy of the body just moving up and down. Then there will be this cross term. It will have a form plus m, 1L will cancel, over 2 y dot phi dot. And then there will be this term. So it will be m L squared over 6 phi dot squared. Yeah. So as I said, this expression can be obtained directly from the rigid body theory, so you will recognize that this is moment of inertia. But anyway, we can do it directly. So we found kinetic energy of the system in motion. Potential energy is easy. Potential energy is, we have only elastic. There is no gravity, so we only need to take into account the two springs. So we take a elastic potential. The standard. This expression for vertical spring, and the another is for the angular spring. This elastic energy. And there is an aerodynamic force, which is a kind of exterior force. So now we will write equation, Euler-Lagrange equations. So Euler-Lagrange equations will take a form, or so the first will be d dt dl dy dot minus dl. So L is t minus u, as usual. Dy, and there will be external force y. And then the same for the angle. So there will be two equations. The left-hand side we already know because we have Lagrangian. The question what we have to put in the external force, because this has to be related to Fa, our aerodynamic force, which is applied in the middle of the plate because of the wind. So now remember how we find these external forces in terms of the force that we know. We use the virtual walk. Remember the principle that we found in the first part of the course is that when in whatever coordinates you write your system, the virtual walk of the force will be the same. So we will write the virtual walk in these coordinates and virtual walk in of the force in coordinate that we know. So virtual walk of the. So what we do, we have this our system, right? So here the force is applied. So virtual work of this system will be Fa by motion of this point. Force is applied to this point. So if this point moves by delta H, then the work will be Fa delta H. But you see, we will compute delta H in vertical direction, and Fa goes in negative direction. So that will be minus. This is our product they look in different directions, so it will be minus. And now remember that what is delta H? Delta H, we know already how to compute. Because delta H is the position of the left-hand side. The change of the position of this point corresponds to the change of position of the left point, plus the change because of the angle. And this is approximately the change due to the angle can be taken as distance. So it's on halfway, delta phi. So the change of the position of the middle can be computed as a change of the left-hand side plus half of the distance multiplied by change of the angle. So it's minus Fa delta y plus L over 2 delta phi. And this is equal minus Fa delta y minus Fal over 2 delta phi. This is one expression, and another expression is that this should be equal to the work written in our original variables, to our chosen variables. So it's f external y, delta y, plus f external phi, delta phi. And the equality should be for arbitrary virtual change of the coordinates, which gives us that this is equal to that, and this is equal to that. Right? So we find that this is minus fa, and this is minus fa L over 2. And you can recognize that this is a force, this is a moment. So that's how you write equation of motion. So again, so the left-hand side is Lagrangian equation of motion, and then we took into account the aerodynamic force, which is defined, and then all we had to do, we use this virtual walk in order to write it for generalized coordinates that we like. So now we can write equations of motion directly. So dl dy dot, y dot comes in these two terms. So what you get is and then the derivative with respect to time. So there will be two terms coming from here. So you just check that the first equation will have form my double dot plus ml over 2 phi double dot. So exactly these two terms, right? M y double dot, but ml over 2 phi double dot. Then from potential, this term will come from potential energy. So it will be plus k1 phi y. And then we have to put on the right-hand side the force minus Fa. And remember that Fa is this coefficient velocity squared phi. Minus C1. Yes. So the second equation will give you, so you should differentiate with respect to phi dot. So it will be ml over 2 y dot. Then the next term ml squared over 3 phi dot, double dot, so second derivative. Then the elastic part gives you k1 phi. And then the force gives you minus Ca LCA v squared phi over 2. That's a question. So what we can do, we put it on the left-hand side, so it will become plus 0. It also become plus 0. And now we write this. So we define vector q as y phi, our two generalized coordinates, and then we can write equations as m q double dot plus, and then there will be matrix which is, let's write it as a sum of symmetric antisymmetric part. So this is correspond to the left part, and this correspond to the second half. So what you get, the mass matrix is ml over 2, ml over 2, ml squared over 3. So this is our mass matrix. It's symmetric. And C plus n is a matrix which comes from this term. So it's K1 Ca v squared. And here it will be, there will be 0. And then K2 plus L Ca v squared over 2. So we are, as promised, we are in the form that we wanted to have. So this is exactly this equation of motion. So we are with aerodynamic force gives us this antisymmetric component to the force. Okay, because matrix is not symmetric, so there will be symmetric part and the antisymmetric part. And antisymmetric, both parts will be, the antisymmetric part will be exactly because we have a wind. So the next point is to find eigenvalues. So eigenvalues you find from a determinant of the writing characteristic equation for this system, as you know how to do. So let's just put it explicitly. So this is 2 by 2 matrix. So we have m lambda squared from the mass, m l lambda squared over 2 here, ml over 2 lambda squared here, and then ml, no, there's no square, ml squared here over 3 lambda squared. So this is a lambda squared m. And then c plus n gives you plus k1. This is 0. This is plus cav squared, and this is plus k2. A lambda v squared over 2 should be 0. 2 by 2 matrix. So remember that this means that the first component 1, 1 times component 2, 2 minus component 1, 2 times component 2, 1 should be 0. This is a definition of determinant for 2 by 2 matrix. Well, you make a product, and I will save time a little bit. Just to, so anyway, what you see that there will be product of these terms minus these terms, and this will be quadratic in lambda squared. So I will just write the final expression. So check. So check that what you get, there will be term with lambda 4. So there will be, let's see. So the lambda squared will come with m squared lambda squared over 12 lambda 4. So this will be from lambda 4. And then there will be term which is proportional to lambda squared. And then there will be the final term you can check that this is what you get after you open the product. And then you solve this quadratic equation. So it's quadratic in lambda squared. So there is this term which we flip and divide by 2. Remember how to solve quadratic equations. And minus this term. This coefficient. And then it will be plus minus square root of this term squared and minus 4 times the product. And so minus, so 4 with 12 cancels, so it will be L squared, m squared L squared over 3 from here. And from here you get K1, K2 plus A squared Boom. So this we usually call discriminant. So this is D. This is our D. And then we have to close. So we found two squared eigenvalues, and totally there are 4 eigenvalues because there will be 2 values here, and then you take one more square root, you get 4 eigenvalues, right, with plus and minus. So now let's see what these eigenvalues are. So essentially what is important is the value of the discriminant. So if it's positive, then we have square root real, and there will be a real part plus minus real number. So they both will be real, and then we take square root of them. But if D is negative, then this part will be imaginary, and there will be real part plus minus imaginary part, and then we still have to take a square root. So there is so essentially the difference, the main difference that we'll see will depend on the value of discriminant. So let's find when discriminant changes its sign. So if D is 0, then these two terms should be equal. So the first term should be equal to the second term. Okay. So mass can cancel, and then you put, so you express, so we need to find V, so we just take this term. So we divide everything by this value, so it will be, and then put K2. So let's express this term. So we express this from the whole expression. 2 equal minus K2 from this. And then the whole stuff divided by the perfector. So we divide plus 3 over L K1 squared. Now we can open the square. It will be L4 over 9 K1 squared plus 2L squared over 3 K2 squared. Two. Here L, this will give you L squared over 3 K1. This gives you 3 cancel, so it will be 2K2. And this gives you 3 K2 squared over K1. And K2 will cancel with 2. So essentially there is this value which is L squared K1 by 3 plus K2 plus 3 K2 squared over K1. So there is a long way, but what is important is that we found it's real positive. And the whole way is just to find that it's positive. Because it is square, which means that we find that V square is just that expression divided by the coefficients, and there is no phi here. why there's phi. Yeah, it's L. VAL. What did I do? V squared CL. Yeah. C. It was L. L. This would be 2 over CAL. And the whole set. It's good to check that I'm correct. And we call it critical. So we have critical velocity, which is taken by this root. So when velocity is critical, is this value, we have discriminant to be 0. Good. So now we are ready. So we are ready to see how eigenvalues change, how they depend on velocity. So the first plot that we do, we will see how the squared eigenvalue, because we have an expression for the squared eigenvalue, and how it changes with velocity. So when velocity is 0, velocity is 0. So when velocity is 0, then just this, so the only place velocity enters is just here. The rest does not depend on velocity. So when velocity is 0, you get two values, and you can check that both you get two squared values, and both of them are negative. You can just put velocity to be 0 and verify that both with plus and minus you get 0. You get something negative. So you have two negative branches, just as we did with. See, that situation is somewhat looks similar in the beginning to our previous gyroscopic system. So there are two negative lambda squareds. But what happened then? Then when velocity is increasing, you see this is a positive value plus something. When velocity is increasing, it comes with minus. So when velocity increases, at certain moment, the discriminant becomes 0, and we know this value. This is exactly the critical value. Very critical. So what happens is discriminant collapses, and just two eigenvalues become the same. So the two eigenvalues, what happens is that the two eigenvalues, they just merge. And when you increase further on, the plus minus term, discriminant become negative. So plus minus term is imaginary, and this is a real part, right? So it doesn't depend on velocity. So what continues is that it continues as a constant. So this is a real part of lambda 1 squared equal real part of lambda 2 squared. So it continues as a constant, just real part. But then we also get imaginary part, which is 0 here, but then it's start to appear from 0 on. So you see that before critical speed you have two negative eigenvalues, squared, real, and after velocity is becoming bigger than this value, you get two complex conjugated eigenvalues with negative real part, but positive or negative imaginary part. Okay, so now we just put it, we take square root of this, and we can put everything to the complex plane. So what we have? So what we have, in the beginning we had two negative real values, so taking real part, they become purely imaginary with plus and minus. So this is a situation which corresponds to velocity 0. So no wind. No wind, everything just oscillates. So that's conservative. So when there is no wind, there is no n matrix, so it's just conservative, stable system. So when we increase the wind, the eigenvalues start to come close to each other. Symmetrically from both sides until they meet. After they meet, they become complex. So square root is just complex, two complex numbers. So one goes to the left, another goes to the right. So the plus minus. So this is what is square root of this picture. And so in the beginning, they on imaginary points, then they meet at velocity equal velocity critical. And this is correspond to velocity bigger than velocity critical. So what you see is that the system is unstable for velocity bigger than velocity critical because we have one of eigenvalue, at least, in fact, in that case, two eigenvalues with a real part bigger than 0. So this is from Lyapunov theorem. So we have eigenvalue on this side. And system is stable for velocity smaller than velocity critical. Yeah. But this is special case. So what we find is that when velocity is not so big, we're stable. When velocity is bigger than certain value that we computed, it becomes unstable. The fact that it's a special case is not so big problem. This can be solved. You can solve by you can add dissipative terms. So the question about special case, you can add dissipative terms, and you will see that everything will move slightly to the left-hand side. So everything will become asymptotically stable. So actually, this stability is all right. So it's a special case, but we can solve it. And we know that at bigger velocity, it's unstable. So essentially, what happens? So what we see? So what we see is that before, so if the velocity is not large, the leaf can oscillate, but it oscillates stably. So essentially, if you have some dissipation, it will always come to the stable equilibrium. Even if the wind is blowing, it will remain stable. So whenever velocity is reaching this critical value, you will start getting the mode, which is exponentially growing. So it becomes unstable. But what you see is that eigenvalues, since the eigenvalues has imaginary part, so the growth of the oscillation will have from the exponentially growing prefactor, but the omega will give you cosine on or sine omega t. So you see that the growing mode will be oscillatory. At that moment, it will be limited by nonlinear terms, but anyway, the instability will be oscillatory. So in the first case, since imaginary part is non-zero, we have oscillations. Oscillatory instability. So this is flutter. This is why we see leaves. So if the wind is not strong, leaves just stay calm, as we see here. There's always wind, so they don't move. But if the wind just passes through some critical value, you will see that leaf start oscillating. So because this oscillation happens, and we get, and the instability occurs through the eigenvalues which has non-zero imaginary part. So this imaginary part gives you oscillations. So that's it. What I want to show, I want to give you the next list and show some videos. So probably I will start with videos, and then we'll see the list. Um segundo. Obrigado. That's some videos just from YouTube. Why doesn't want to give a sound? Okay. So that's videos from YouTube, and this is these are videos from some NASA experiments. So essentially, you can think of a leaf. Instead of leaf, there are many other systems, right? So you have a curtain which is can make oscillations, but at the same time, the same happens with airplane wings. And this was a very big problem in the beginning of the 20th century, like in the years 20s, more or less, because after the plane was invented, it was made of wood. And initially, the problem was to make an engine to fly faster. And then they succeeded to make very good engines. So the airplane started to fly very fast. And what started to happen is this phenomenon. So velocity passes through critical value. It starts oscillating. And oscillations are very violent. So essentially, what was happening is that the plane was just broken apart in seconds. And during 20s, 30s, this theory appeared. So they started to understand how to make what is the reason for this instability, and essentially the answer was you have to make wings stiffer. So you will see that this critical value. So in order to increase critical speed, you need to increase stiffness of the springs. So these wings should be stiffer. So they started to do them out of aluminum or the metal, so the metal is stronger. So and here you see you will see many different examples of similar structures, how they interact with the wind and become unstable. So I will jump the first part because I will show a different example, but. You see, it's all oscillating. You see, that's. Oof. Well, so essentially, this is just to say that the design of airplanes always take this into account. So this should not happen. Okay, and then the other example that probably interesting to see is happened with a bridge. So this is a famous case which was later investigated with different hypotheses, but the final decision is that it was exactly flatter. So it's Tahoma Bridge. The good part is it was very well documented. So there are videos and documents. And so what happened is this bridge which was created started to oscillate. And the oscillations are because of the wind. So it's exactly the same system. So wind is blowing, and you have motion up and down and angle rotating. So going up and down and angle. So that's very much the same system that we considered, just slightly more, it's more complex. And just simple wind is creating these oscillations because stiffness was low. So wind very strong start to make this system to be unstable. Well, there are some funny. So what? Something is broken here. So you see that's going up and down slightly, right? And rotating. So that's a combination of motions together with aerodynamic force make it unstable. Interesting is that wind can do this thing, right? Essentially the same thing as a leaf moving on the wind. So there is one thing that I want to get. Okay. Okay, everything breaks. So. So that ends the part of the oscillations with time-independent forces. And I will give now the list. So I promise I will photocopy my hand notes and put only. They also can have mistakes. So today I'll give you the exercise list. So I think it's 4 now. So the exercise. List 4. And this must be for the next Monday. So the next Monday is So February 6th. Okay. So the first problem is you take a matrix and take it like 3, 1, 0, 0, 3, 0, P, 0, 3, where P is a parameter. So what you have to do is find a general solution of the problem x dot equal ax for p0. So in case of p0, so just put 0 here and then just find a general solution. B, find eigenvalues and eigenvectors for P non-zero, for any P non-zero, eigenvalues and eigenvectors. And then C is show how eigenvalues and eigenvectors, eigenvalues move on a complex plane as P changes from negative to positive. So this last thing is that you draw a complex plane, and then there is some free eigenvalues, right? Lambda 1, lambda 2, lambda 3, and you should see how they move on the complex plane when you increase P. This is problem 1. So the problem 2. Problem 2. Let's consider this Lagrangian of the L Lagrangian of the gyroscopic system. So Lagrangian function of the gyroscopic system, which is, as we already showed, has this form. So there is kinetic energy plus mixed term between velocities and coordinates and minus potential energy. With mass matrix symmetric, gyroscopic matrix antisymmetric, and that matrix of potential forces symmetric. So it's gyroscopic system. I will continue here. So using our Noether theorems, prove that the energy, remember by Noether theorem, the energy prove the conservation, prove that the energy which is conserved, right, automatically. So energy which, there was a formula which is dl dq I dot q I dot minus L. Remember that formula. So that was the energy for arbitrary system with Lagrangians that does not depend on time, which is the case here. So prove that whenever you do this, what you get is this. So just potential plus kinetic plus potential energy. So this intermediate term disappears. And this changes from minus to plus. So essentially, this system, when you rotate this system with gyroscopic force, it conserves energy, which is exactly the same energy as you get as energy without gyroscopic forces. Okay, so just make this computation and show that the energy is the same. And this is convenient thing because automatically, as you have the energy in this form, for example, if C is positive definite, you can prove that even though for gyroscopic system you are in a special case, it's stable. Just the same as you did with a conservative system without gyroscopic forces, just from a minimum of energy. Okay, and then the third problem. What you do? You consider the wind blowing from opposite direction. Okay, when the wind flowing from opposite direction, force will be directed upwards, right? Because if wind is here, so if wind is from the left, it will be pushing it down. If it's from the right, it will push it up. So the same force, but turned in a different direction. So that's an example which will be called divergence. So what you have to do here, so write equations of motion. Essentially, you have to repeat the whole derivation, but with opposite force, right? Before the force was down, now force is up. Not a big difference. B, compute eigenvalues. Also will be similar formula, but different, because some signs will be different, so some values will be different. And C, analyze eigenvalues as functions of speed v. Analyze how the eigenvalues change as a speed change. So essentially, you should see what will be change on these pictures with lambda square and then with the square root. So the pictures will be quite different. And you should be very careful here because most of the people do mistake, very simple algebraic mistakes here, because you should be careful with signs. And then from this analysis, D, you analyze stability, which means that you have to find critical speed and its interpretation. And here what you can see, so what you should kind of derive. So whenever you have a leaf, as we discussed, right? So you have a leaf on a wind. So if you support it, so if the wind is blowing from the support point to the end, so from the support point to the end, we have flutter, oscillator instability, which you can just see. So at a small speed, nothing happens. But if the wind is stronger, you have a flutter. But if the wind is blowing in opposite direction, so again, if the wind is very weak, nothing will move. But if the wind is stronger, so you see it just breaks, right? It just goes up. So there will be no oscillation. So that's why the first case was called flutter, but this case is called divergence. So what you will see is that there will be critical speed, but the instability will not be oscillatory. So this is what you have to find from there. So that's quite an interesting exercise. So that's it. And tomorrow we should go to the part B of the oscillations already, when there are forces or there are terms which depend on time. There will be just small part in the beginning which is still not on the nodes, but then I will continue following the PDF file that you can find on the web page. Okay, so we're late, but see you tomorrow. Thank you.